In this presentation, the role of Geographic Information Systems (GIS) in ecological planning and urban resilience processes is examined through 3 implemented case studies. In the Copenhagen case, GIS was used to spatially analyze flood risks and to guide the design of blue-green infrastructure. In Singapore, GIS supported the evaluation of green infrastructure and microclimate relationships within a high-density urban environment. In the Melbourne case, GIS functioned as a key decision support tool for planning and monitoring nature-based solutions aimed at mitigating the urban heat island effect. Together, these 3 examples demonstrate how GIS operates as a common tool that contributes to the management of environmental risks and supports planning approaches aimed at enhancing urban resilience across different urban contexts. The case studies examined in this course focus on the use of GIS in ecological planning and urban resilience processes. The selected cases represent different urban contexts and environmental challenges, allowing for a comparative understanding of GIS-based planning approaches. Copenhagen, GIS and remote sensing-based case study. Singapore Gardens by the Bay, green infrastructure and microclimate. Melbourne, urban forest and heat mitigation. By the end of this course, students are expected to analyze how environmental risks and urban challenges, such as urban flooding, microclimatic stress, and the urban heat island effect, are examined and addressed in GIS-based spatial analyses, interpret GIS-based datasets and analytical outputs presented in case studies to evaluate spatial relationships between natural systems, the built environment, and environmental performance. Evaluate the contributions of nature-based and green infrastructure solutions, including blue-green infrastructure, large-scale urban landscapes, and urban forests, based on case study evidence, in relation to climate adaptation and urban resilience. This slide presents the background of urban flood risk in the city of Copenhagen. In particular, the extreme rainfall, cloudburst, events in 2011 and 2014 resulted in widespread urban flooding due to the high intensity of precipitation occurring over short periods. During these events, conventional stormwater drainage systems proved inadequate to cope with the intensity and volume of extreme rainfall. Once the design capacity of the existing infrastructure was exceeded, system performance declined significantly, leading to an increased flood risk. As a consequence, transportation infrastructure, buildings, and public spaces across Copenhagen experienced severe damage, accompanied by substantial economic losses. These events demonstrated that flood risk is not solely a technical infrastructure issue, but rather a multi-dimensional challenge that must be addressed at the spatial planning and urban design scale. Within this context, the need for GIS and remote sensing-based, spatially integrated planning approaches became evident, and the cloudburst management plan was developed accordingly. GIS and remote sensing techniques were used to identify flood-prone areas and priority catchments across Copenhagen. Flood risk zones were mapped by integrating topography, drainage patterns, and hydrological catchments within a GIS environment. This analysis enabled the classification of the city into low, moderate, and high flood risk zones and supported the selection of high-risk catchments for detailed intervention. By spatially visualizing flood exposure at the city scale, GIS provided a clear basis for targeted planning decisions and the development of the cloudburst management plan. GIS transforms urban flooding from an unpredictable event into a spatially identifiable and manageable risk. In this stage of the Copenhagen Cloudburst Management Plan, GIS-based datasets were produced to analyze the ground conditions of the city in a systematic way. First, a terrain model was used to understand slope characteristics and elevation differences, which directly influence surface runoff behavior during extreme rainfall events. Second, sub-catchment areas were identified in order to assess potential flood-prone areas and to trace catchment water routes across the urban fabric. This allowed planners to understand where water accumulates and how it moves through the city. In addition, a mobility corridors map was produced to identify major residential and commercial activity areas, ensuring that flood risk assessment was directly linked to daily urban functions and critical infrastructures. Maps processed in a GIS environment were overlaid to analyze conditions and develop site-specific solutions aimed at reducing flood risks caused by extreme rainfall events. GIS analyses contributed to the development of low-tech solutions. Within this framework, cloudburst roads were identified, green roads were designed, water detention streets were planned, water detention areas that function as public amenity spaces during dry periods were created. Overlay analyses enabled the identification of spatial interventions that follow natural drainage patterns. This visual illustrates the GIS-based multi-layer analytical framework of the Copenhagen Cloudburst Management Plan and demonstrates how these analyses are translated into planning decisions. In essence, it provides spatial answers to the questions: where is the risk? Where does the water flow? And which areas should be prioritized? Natural flow and drainage routes. The upper maps illustrate surface runoff directions and the natural paths followed by water, indicating where cloudburst roads should be located. Flood risk distribution. Flood risk across the city is spatially classified into high, medium, and low risk zones. Prioritization. The central maps distinguish areas with high intervention priority, based on the overlap of high flood risk and intensive urban use. Social justice dimension. The lower right maps highlight high-risk areas that were previously not prioritized, and reveal their overlap with socially vulnerable areas. Link to planning decisions. By reading all layers together, site-specific planning decisions are produced for cloudburst boulevards, water detention streets and areas, and integrated blue-green infrastructure networks. This visual illustrates how low-tech, multifunctional flood management solutions developed within the Copenhagen Cloudburst Management Plan are integrated into urban design. Based on GIS-based analyses, identified natural drainage routes are reconfigured through urban open spaces and street sections. In this approach, water is not treated as an invisible underground infrastructure element, but rather as an integral component of urban space. The visual present solutions developed for different urban topologies, including parks, plazas, streets, green streets, urban creeks, and retention boulevards. Under normal conditions, these spaces function as public amenity areas, while during extreme rainfall events they transform into temporary water retention and conveyance areas. As shown in the sectional perspective, roads, sidewalks, green belts, and retention channels are designed together, enabling the integration of blue-green infrastructure into the urban fabric. The controlled conveyance, storage, and slowing of stormwater are achieved through spatial design decisions. This example demonstrates that GIS analyses do not merely produce risk maps, but operate as a decision support system that directly informs street sections, open space design, and the quality of public space. In the Copenhagen case, GIS transforms flood risk from a purely technical engineering issue into a designable, multifunctional urban infrastructure element that generates public value. This case demonstrates that GIS functions not merely as a tool for mapping existing conditions, but as a decision support system that anticipates risks and guides spatial interventions. In the Copenhagen example, extreme rainfall is addressed not only as a technical infrastructure problem, but in relation to the city's topography and drainage structure. Through GIS-based analyses, surface runoff, low-lying areas, and natural drainage corridors are evaluated together, clearly revealing where flood risk is concentrated. This spatial understanding highlights not only the location of risk, but also how it can be managed at the urban scale. As a result, planning and design decisions are developed through the organization of urban space rather than relying solely on engineering solutions. Overall, the Copenhagen cloudburst case illustrates that GIS strengthens the link between analysis and decision-making, enabling the development of data-driven, spatially responsive, and scenario-based urban interventions for climate adaptation and resilience. This slide introduces Gardens by the Bay, one of the most significant implemented urban nature projects in Singapore. The project represents a strong case study demonstrating how nature can be reintroduced and integrated into public life within a highly dense urban environment. Gardens by the Bay is not merely a park or a recreational area. Rather, it is a comprehensive urban landscape project in which green infrastructure, ecological processes, and public space are addressed in an integrated manner. This holistic approach was supported throughout the project by GIS-based spatial analyses and environmental performance assessments. Within the context of Singapore, a city characterized by high density and limited land availability, These analyses contributed to shaping decisions related to site selection, green space configuration, and microclimate regulation. Consequently, Gardens by the Bay provides a clear example of how GIS functions not only as a mapping tool, but also as a decision support and monitoring system in implemented nature-based projects. How did GIS provide the analytical foundation? In the Gardens by the Bay project, Geographic Information Systems, GIS, did not function as a tool for direct formal design production. Rather, they established the analytical foundation upon which design decisions were based. Given the location, scale, and environmental context of the project area, spatial decisions required the integrated evaluation of multiple environmental and urban datasets. Within this framework, GIS first enabled a comprehensive analysis of spatial data such as land use, reclaimed areas, and shoreline configuration. These analyses supported the interpretation of the site's relationships with both natural and built systems, informing decisions related to site selection and overall spatial organization. Topographic data derived from digital elevation models, DEM, were used to assess slopes, elevation differences, and spatial visual relationships, which in turn guided the placement of green areas and the configuration of circulation systems. The analytical role of GIS became even more evident in the assessment of vegetation and ecological layers. The spatial distribution of vegetation types, existing green areas, and their connections with the surrounding park system were analyzed, allowing the project to be considered not only as an isolated site but as part of a broader urban green network. This approach ensured that green infrastructure continuity became a core component of the design strategy. In addition, remote sensing-derived indicators such as INDV and land surface temperature, LST, enabled the evaluation of the microclimatic effects of green areas. Through these analyses, planting strategies were grounded not merely in aesthetic considerations but in measurable environmental performance criteria. As a result, the design evolved as a nature-based solution aimed at mitigating urban heat island effects. Following implementation, GIS continued to function as a monitoring and management tool. Spatial monitoring of vegetation health, maintenance zones, and visitor flows made it possible to assess the project's long-term environmental performance. In this respect, GIS in the Gardens by the Bay project operated not only as a pre-design analytical tool, but as a comprehensive decision support system linking planning, implementation, and post-implementation phases. Gardens by the Bay integrates vegetation, structure, and climate-responsive systems to create a nature-based urban landscape. Environmental and spatial analyses inform the design to enhance microclimate regulation and urban resilience. This case study clearly demonstrates that geographic information systems are not limited to map production. Rather, they function as integrated systems that support analysis, decision-making, and monitoring throughout the planning process. In the Gardens by the Bay project, GIS was introduced from the early stages of planning, enabling the integrated evaluation of spatial and environmental data. Different data layers, such as land use, coastal areas, topography, vegetation, and environmental context, were brought together within a GIS environment. This approach ensured that design decisions were developed on an analytical basis rather than through intuition alone. Within this process, GIS played a particularly critical role in the integration of nature-based solutions into planning. Decisions related to green infrastructure configuration, ecological continuity, and microclimate regulation were assessed through spatial analyses, allowing the development of climate-responsive design strategies with improved environmental performance. In this respect, GIS functioned not merely as an analytical tool, but as a decision support system that actively informed design strategies. Following implementation, GIS continued to play a key role in the monitoring and evaluation phase by enabling the assessment of long-term environmental performance. Spatial monitoring of vegetation health, land use patterns, and environmental impacts made it possible to review planning decisions over time and adapt them when necessary. Through this capability, GIS transformed planning from a static intervention into a dynamic and adaptive process. In conclusion, the Gardens by the Bay case illustrates that GIS is a fundamental planning tool that strengthens nature-based solutions, supports environmental resilience, and enables evidence-based decision-making in ecological planning. This example clearly highlights the essential role of GIS in developing sustainable and resilient spatial strategies, particularly within high-density urban contexts. In this section, the role of Geographic Information Systems, GIS, in ecological planning and urban heat mitigation processes is examined through the case of the Melbourne Urban Forest Strategy, which represents an implemented example. The Melbourne Urban Forest Strategy has been developed to address challenges such as the urban heat island effect, climate change-related environmental stressors, and biodiversity loss, and it is being implemented at the city scale. This strategy is not approached merely as a conceptual vision or policy document. Instead, concrete spatial interventions, including tree planting, canopy expansion, and the strengthening of green infrastructure, are being implemented on the ground. One of the core components of this process is that these interventions are being guided through GIS-based spatial data and analytical processes. GIS is being used as a primary decision support tool to identify areas that are more exposed to urban heat, to detect locations with low canopy cover, and to define priority zones for tree planting. At the same time, the monitoring and evaluation of environmental impacts following implementation are also being carried out through GIS. In this context, the Melbourne Urban Forest Strategy is considered a strong case study demonstrating how nature-based solutions within ecological planning are being made implementable, monitorable, and sustainable through a GIS-supported analytical framework. This slide presents GIS-based spatial analyses developed within the framework of the Melbourne Urban Forest. The maps were produced to evaluate the structural continuity of green infrastructure and ecological connectivity across the city of Melbourne. The city-scale map on the left was generated by integrating different vegetation layers, such as tree canopy, mid-story, and understory vegetation, within a GIS environment. Through these analyses, ecological corridors connecting parks, waterways, and green spaces, as well as areas where this continuity is fragmented, can be spatially identified. The detailed map on the right illustrates how this analytical approach is applied at the street scale. Street trees and mid-story vegetation contribute to strengthening connectivity by functioning as ecological stepping stones between larger green areas. These GIS-based outputs are used not only to describe existing conditions but also to spatially guide future tree planting and green infrastructure interventions. In this way, GIS provides an analytical foundation for planning decisions aimed at strengthening ecological connectivity and enhancing urban resilience. These visuals illustrate the spatial manifestation of planning decisions implemented on the ground within the framework of the Melbourne Urban Forest Strategy. The images demonstrate how tree planting and green infrastructure interventions have been applied across different urban contexts. The interventions carried out along streets, pedestrian corridors, and building interfaces indicate that the urban forest strategy is not limited to large park areas. Rather, it adopts an approach that extends throughout the everyday urban environment. In this slide, the role of GIS in addressing urban heat stress and enhancing urban resilience is highlighted. GIS-based analyses demonstrate that areas with dense vegetation tend to exhibit lower surface temperatures. This spatial relationship provides clear evidence supporting the effectiveness of nature-based solutions in mitigating the urban heat island effect. Based on these analyses, tree planting and green infrastructure interventions are strategically prioritized in locations with high heat exposure and low canopy cover. In this way, GIS supports targeted and efficient interventions that strengthen the climate adaptation capacity of the urban environment. Furthermore, GIS plays a critical role beyond the planning stage by supporting post-implementation monitoring and evaluation processes. Through continuous spatial analysis, the long-term impacts of green infrastructure investments on urban resilience can be assessed, allowing planners to evaluate performance and adjust strategies over time. Overall, this case illustrates how GIS functions not only as an analytical tool, but as a comprehensive decision support system that links spatial analysis, implementation, and long-term resilience planning. In Copenhagen, GIS supported spatial design decisions aimed at reducing flood risk. In Singapore, GIS-based analyses were used to address the relationship between green infrastructure and microclimate. In Melbourne, nature-based interventions targeting the mitigation of the urban heat island effect were guided through GIS. Together, These case studies demonstrate that GIS operates with a similar planning logic across different urban contexts. In each example, GIS transforms environmental data into spatial analyses that support implementation-oriented and resilience-focused planning decisions. This summary highlights GIS as a key decision support tool that makes environmental risks spatially visible across different urban contexts. Through GIS-based analyses, nature-based solutions are effectively targeted, supporting urban resilience and climate adaptation. GIS brings together analysis, implementation, and monitoring within an integrated and evidence-based planning framework.